Hello students, so here we have the geometrical optics lab in which we're going to look at the reflection of light from a plane mirror, a concave mirror and a convex mirror. We're also going to look at the laws of refraction. There are some initial setup required. You take a piece of paper, draw a line, and then you have to draw a line perpendicular to that using the protractor. And then at equal distances, you're drawing lines parallel to that. So here is how the protractor is placed to get the perpendicular. And then you also have to draw two lines at an angle of 30 degrees, another at 40 degrees. So that is what I'm showing now. So you got those two lines at 30 and 40 degrees. These are the incident rays. And here you have a set of parallel incident rays. So we need several copies of these two setups, as you're going to see. So basically what I have here is I have set up the laser. I have sort of laid it down horizontally on the table. I have a paper on which I have already drawn the lines, as you can see, a line here, and using a protractor I have drawn a perpendicular. So first I marked a point on the line and placed the protractor, and I've drawn a line at exactly 90 degrees. That is called the normal, or the perpendicular, of course. And then I drew two lines, one at 30 degrees and the other at 40 degrees, as you can see, and these are going to represent the incident rays. Next, I take the mirror, or the mirrors, actually three sides. You have the plane, the concave and the convex. Try not to touch those surfaces. And then first I place the plane surface right on the line that I've drawn, exactly on the line that I've drawn there, as much as possible without touching the surfaces. And if you want to use tape to keep the mirror from moving or the paper from moving, that's okay. In fact, that will be more convenient. And then you can move the laser and set it in such a way. See what I'm doing? I'm just trying to tilt it so and move it, so look at that, so that the laser beam is passing right at 30 degrees, as you can see. And then you get the reflected ray. And when you get the reflected ray, get some points on that. I got 1 point there and maybe a second point. Actually 2 points are enough. Look at that. And you have your reflected ray. And you can do the same for 40 degrees by moving the laser and adjusting it. Now take time to adjust that so it's right on the line that you've drawn. A little bit more, I think. Okay. So you see that it's now at 40, and I should try to get the same thing. You should try to get the 2 points. So once you get those 2 points, you can join the points to get the reflected ray. So get the reflected ray for both of them. This is the reflected ray for the first one that I am getting now. Use a sharp pencil so you get the lines correctly. And what you got to do is you got to measure this angle and check if that is equal to the angle of incidence. So that is in the first part. All right, now what you're seeing is I've already drawn the lines, and you can see those lines, parallel lines at equal distances that I've drawn. And I have taken the concave surface and kept it in such a way that the edges are exactly touching the line that I've drawn. And then I can hold it and trace out the concave surface, which I've done now. And if it moves, you gotta put it back and do it. Okay, so that is the setup that I have now, and you have to move the laser source closer, incline it again, and adjust the angle so that it, let's say, I will now move it to this line. You see, you're trying to make it incident exactly on the line that you've drawn. So that is the incident ray. And once it's reflected, again, you got to get 2 points. All right, so let me get my first point somewhere here. And you have to be careful that you're not cutting out the laser beam. And then let me get the second point somewhere here. Okay, so I've got my 2 points. Now move the laser to a position where you get it over the second one that you've drawn. This is the second one. You'll have to be very careful about the angle and the position, you see. And it's a little bit tricky, but you can do it. Okay, make sure it passes right on the line. Okay, so here it's okay. There you go. So a little bit more. It is not easy unless you're very careful. Okay, now that I think I got it. Okay, so get the reflected one for that. So once again, I need at least 2 points. So keep the pencil vertical and try to get that point and try to get a second point. You see that the second point is exactly where it was before. Okay, so do that for all the rays, including the middle. The middle one will come straight back. The middle one, see that it's going to come straight back. And the next one, you can see if I, okay, a little bit more. So you see that. Depends on how well you adjust it. All right, there. So now I got my second point there, and again it's passing through that. Continue that for all the 4, and then we can get the reflected rays. This one right there. This is the reflected ray of that. So you see that all of those reflected rays converge to a point, and actually this point is called the principal focus. And this is the pole of the mirror. So P to F is the focal length. Now for the convex surface, you do the same thing. And see, I'm just showing it for one incident ray. And I figured out that if you keep the laser closer to the paper, it becomes even more easier. So make sure that you've adjusted the position and the angle so that the ray passes over the line you've drawn. And then you see the reflected ray. Mark the points very carefully. Use a sharp pencil, and everything will be good. So do the same for all the rays. And after that, after you've taken out the mirror, what you do is you trace out the rays, because it's reflected. The first one is reflected this way, so you put a, let me use a pen so it's clearer for you to see. So these are the reflected rays. See that this is going to go straight back. So you see that the reflected rays are diverging, and if you extend these reflected rays back, as I have done, you extend them back, they all appear to be coming from this point, which is actually the principal focus. So this is the pole, and P to F is the focal length of the convex mirror. So that's how you do that. So next we're looking at refraction, and you can see I have already, oh, there is something you need to do. Now I've drawn the line at the edge of the paper, but please make this line in the middle of the paper. Make this the line, and you will see why. And take that semicircular plate that you're given, a semicircular lens actually, and keep it on that line, trace its outline, which I've already done, and situate the laser so that it goes exactly over the 30 degrees incident ray. And when it falls on the lens, you see that a part of it is reflected. We're not concerned about the reflected part because that's coming from the front face. We are more concerned about the refracted part. So let me see if I can, you can see the light coming through the lens. That's what we're looking for. So as close to the lens as possible, put a point, and then get other points that are away. So I got 3 points now, as you can see. And then what you got to do is you remove the lens, and all right, we don't need the laser now. So remove the lens and draw this line. This is the refracted ray. And this is why I wanted you to draw it near the middle of the paper, because it's at the edge. It works, but it's better if you draw it at the middle of the paper. So extend the normal or the perpendicular so you can measure this angle. So this is the refracted ray, and you got to measure this angle. And you can see that that angle is less than 30 degrees. So find what that angle is, and then you can calculate the refractive index of the material of the lens using equation number 1, where N1 sine theta 1 is equal to N2 sine theta 2, where 30 degrees is sine theta 1. N1 is the first material, which is air. Its refractive index is 1. So 1 sine 30 is equal to N2, which we do not know. That's the refractive index of the material of the lens, sine of whatever angle you got here. So plug in that number there, calculate the refractive index of the material of the lens. All right, in this part of the lab, we have the, oh, this is moved. We have to have the lens placed with its flat side on the line that we've drawn. Try to situate it correctly. Okay, right there. And then, see, this is the line drawn at 30 degrees. So the ray should fall at the center of the lens. The center of the lens is this part. The center of the curved part. It should fall at the center of the curved part. So now right there, okay, so there. But yet it should be parallel to this line. So you see that? Falling at the center, but parallel to this ray. So this is about 30 degrees angle. And you see that it's coming out the other side clearly. It's coming out the other side here. And then what we got to do is we have to always make sure that the ray is falling at the center, but tilt the laser so that you increase the angle. And each time when you do that, you observe that this refracted ray is turning further and further away, as you can see. So let me keep moving it, and you will notice the difference. See that? The ray, and I'm changing the angle. You can bring it closer, but make sure that it's always incident at the center here. And be careful that nothing moves. And then keep on increasing the angle, and you see now that the ray is becoming more and more parallel to the flat surface. All right, so we got a long way to go. So now you see the ray is there. Okay, let me move it closer. I'm changing the angle further. Okay, it should fall at the center now. A little bit more. Okay, it's almost parallel. There it is. It's now about parallel. Now we got to slowly increase the angle in steps. There it is. And you also notice that the reflected ray is getting stronger. So we have to find that angle at which the refracted ray completely just vanishes. You know, it's about to vanish. Now you can see it's light there. And then always make sure it hits the center. A little bit more, it's still there. I'm changing the angle now little by little and trying to find out the point at which that parallel ray almost vanishes. Okay, it's gone. Now you see that it's just gone. So that's when you trace this line. You see, I've already traced it. Here it is, this line. And then we got to remove this and measure. Okay, don't do freehand. Use a ruler, and you got to measure this angle. So that's the critical angle. So measure that. Now, in order to find the focal length of the convex lens, you take the convex lens that as I have done and keep it on the line that has been drawn. So situated on the line. Okay, so that's the convex lens situated on the line. And then place the laser close to it in such a way that the light falls on the line that you've drawn in the center. So that is the light that's falling right on the center. Adjust the angle, you will see that it'll pass through undeflected, so it's just going through the lens. Again, get those 2 points, get any 2 points so you can trace the ray. Then move it to the next one. Again, make sure it's falling on the line. So make sure it's passing on the line a little bit more. Yeah. Okay, and then you see, okay, that's the incident ray. There you see the incident ray. Then you see that it's bending. So situate 2 points or maybe 3 and all the way here. Okay, so it's passing through that line. And then on the other side, do the same thing. On the other side, now try to do the same thing, okay? Now don't rush here because it's very important that the laser beam falls on the parallel ray that you've drawn, and then get 2 or 3 points like before. This looks like it's going to go out of the paper. Okay, you can even do it with these. Let's see. All right. Yeah, it's going out of the paper. So it's better if you actually draw this line in the center. You see, it's not exactly in the center. That's why it's going out of the paper. Okay, I hope you understand that. So it's going out of the paper. See? So technically, after you've done that, what you will do is you will take this and you will draw those lines from the center, trying to see where all these lines intersect. Now those are the refracted rays that intersect there, and unfortunately for me it's going slightly out of the paper, So you have to make sure that the line is drawn at the center of the paper to avoid that. Okay, well, I just got it. So this is the focal point where they all come together. Be careful, you got to draw the arrows to show those are the refracted rays. And if you do the same for this, you will get the rays like that. Okay. Do not draw freehand, please draw it with a ruler. So you get all those. And this is the center of the lens. Actually, it's called the optic center. So O, and that's F. This is the focal length. This is what you mean by focal length of the lens which you need to measure. Now, do the same thing with the concave lens, but here you got to be a little bit more careful. Because when you have the ray fall on that line, as you can see, a part of it will be reflected, so don't go with that. But we're looking for the refracted one, which is actually on this side. You know, this one, don't go with the reflected one. That is the refracted one. Was it falling correctly? Yes, it was. Okay. So the central one, it's going to go straight. It'll pass through straight. You can see that. Okay. And then do this on all the rays. Be careful about those. You can see that it's bending away. Get those. Likewise on the last two rays, it's bending more now. And on the last one on this, see, I'm doing this fast for the sake of not making the video too long, but you got to do it a little bit more carefully. And then after you're done with that, remove the convex lens. You can actually draw the outline of the convex lens. Could do the same thing with the concave lens. You can do the same thing with the convex also. And then what you do now is you see that here are the refracted rays. Join all the refracted rays. This one was going straight. And if you do it really carefully, you'll see that all of these rays appear to be coming from one point. So the rays are going away, they're diverging, but they all appear to be coming from the focal point. So that's the optic center. This is the focal length. This distance is the focal length of the concave lens. So that's what you got to do. So let me show it to you. Maybe it's a little bit clearer with this. See how the rays are all going away. And then when you extend them backwards, each one is extended backwards, they appear to be coming from here. So that is the focal point. And so the focal point of a concave lens is virtual, while the focal point of a convex lens is real. And so it did take me a longer time to do this lab, especially because I had to be recording at the same time that I was doing it. And that is obviously why I couldn't do it so accurately. But you should try to pay attention to what you're doing so that the lines are all drawn with a sharp pencil. And if you do all that, then it's going to be a good lab.